Before we can start talking about light, we want to make sure that we know what light is, right? This was a very complicated problem, a difficult problem for science for a long time. If you think about the earliest, if you look at the earliest things that people said about light, most of the people who care to think about light thought that it was probably particles of some kind of substance. In Hinduism and some Buddhist texts, they talk about particles of fire. In Greece and in Rome, also people favor the interpretation or the idea that light was made of little things that are traveling very fast. So that was sort of the consensus until pretty much the 17th century, the 1600s, where this is the first time that at least somebody important said that he didn't think that light was made of particles. This is Descartes, and he said that actually he preferred to think of light. He thought it was a good idea to believe that light was actually sort of a mechanical vibration, just like sound was. He was thinking about sound, and he thought that light was probably just like a sound wave. So in a sound wave, what you have is a medium that sort of creates a disturbance. It vibrates, it shakes the particles of the medium, and then that vibration just propagates, as we have been discussing, right? So Descartes thought that light was the same, should be the same thing, that a light bulb, he didn't have light bulbs, a candle, with the molecules in this candle, basically they were shaking some sort of medium, not air, of course, but some sort of medium, and that this mechanical vibration got propagated very quickly, and that was light. That was the first time that people started to think about light as a wave. But then came Newton, and he didn't like the idea of light being a wave. He thought that it should be particles. Whenever you see the shadow of an object, when a light is shining on an object, you see sharp edges, right? You can follow from the edge of the shadow, you can go to the object, and that's a straight line that goes all the way to the sun. So for him, when you see a light ray coming through the window in your room, you also see this straight line light propagating in a straight line. So he thought it doesn't make sense that light would be a wave, for a simple reason that they already knew at that time that waves, for example, tend to move around objects. If you send a wave, say an ocean wave, and there is a big boulder near the beach, then the wave comes in and it sort of hugs the boulder. It doesn't leave a perfect shadow of devoid of waves behind the boulder. It actually, there's a region where there's no waves, but they kind of start getting together behind the boulder. So Newton knew that that's what waves did. That if you pass a wave through a small obstacle, on the other side it's going to expand. We're going to talk about that's diffraction. So he said definitely it's not going to be a wave, it should be a particle. Because of the stature that Newton had for a long time, that he still has, I guess, but with his contemporaries, people believe that. Of course, he didn't have any, there were no definitive experiment that would prove that he was, at that time, that would prove that he was right or that he was wrong. So people just believed him. So for 100 years, that was the theory about light being made of little particles of something. That was what people believed. But then the definitive, the experiment that really pointed in the direction of, in a different direction, not just speculation like Descartes had said, that it should be a wave and that's it, was Young. He did an experiment in the 1800s, and basically what he did is what you can see back there in the room. He passed light through two slits. That's what I have here in this little device. I have two slits. Actually, I'm pointing it in a different place. Let me move it back to the two slits. So he passed light through a screen that had cut out. He had cut out two little slits, right? And he was looking at what happens on the other side. So if the light, he didn't have a laser, if this was not here, you would see just one spot on the screen, on the wall behind you. That's what the laser light looks like coming out of the laser. But once it goes through the two slits, that's the pattern that you see. And that pattern, it's very, very hard to understand. It's impossible to understand it if you think that light is propagating, if it's particles propagating in straight lines. That is impossible, and I'll show you that in a minute. So the pendulum went the other way, back the other way, and now people started to believe that light was actually a wave. There was a very clear evidence that it was. The nail in the coffin was put by Maxwell because he found out that what kind of wave was light. That was not known. Okay, light is a wave, but what kind of wave? Nobody knew that. Maxwell, by playing with the equations that describe electricity and magnetism, playing with those equations, found that there was this thing that was a wave made of electric fields and magnetic fields propagating in space together. And when he calculated what the constants were there in his equations, when he calculated the speed of this wave, he found that it was 3 × 10⁸ meters per second, which was the already measured speed of light that coincided with the measured speed of light. So the conclusion was light is an electromagnetic wave, right? So at that point, we knew for sure that light was a wave and that it was an electromagnetic wave, and we could do calculations and so on. So the pendulum is back to the wave camp for a while, about 50 years, and then in 1900s come, and it goes to the other way. Because Einstein, there were already some experiments that were showing that if light just propagated as a wave, it would be impossible to have something called the photoelectric effect, which is you shine light on, you have a tube with a cathode and anode, you put some difference in voltage. If you don't shine light on it, nothing happens. But as soon as you start shining light of the right frequency, you start getting electrons jumping from the anode to the cathode, whichever is the one that emits the electrons. And that, when you do the numbers with the wave theory, that's impossible. If you want to read more details about that, you can look in the book. There's a chapter about that. It is completely impossible. So the wave theory of light was failing in that kind of experiment, and Einstein came up with a way of explaining the photoelectric effect, which involved going back to Newton's theory of particles, of light propagating or being made out of these packages of energy that propagate really fast in space. So where do we stand now? Well, with quantum theory, we actually were able to, I wouldn't say cheat, but the answer to the question of what is light is actually, it is a particle and it is a wave. It's both things. And with quantum theory, physicists go further than that and said everything has a dual nature of particle and wave. You are a particle, you behave as a particle when you're running, when you're in your car moving at 60 miles an hour and so on. When you hit a wall, you behave as a particle, right? You don't penetrate the wall and so on. But in certain circumstances, matter can behave as a wave. And that's been confirmed in many, many experiments. So the answer to this very ancient question of what light is, some people thinking it was particles, some people thinking it was waves, is it is both.